Thank you very much. Thank you very much. I'm going to share the screen. Okay, can you see the screen?
Yes, we can see the screen.
Okay, nice. So good morning, everybody. My name is Francesco Enrichetti. I'm a marine biology researcher from the University of Genoa. And today I have the pleasure to present an overview on the ecology of abandoned nets in the Mediterranean Sea within the EcoeFISHent Advanced Training Course in the module of Blue Circular Economy. Here you can find a summary of the topics we will discuss today within the next 2 hours. We will first introduce some basic concepts as marine litter, sources of marine litter, distribution, methods of study, and definition of ALDC FG, type and composition of fishing gears. Then we will see which are the reasons why fishing gear is abandoned, lost, or discharged. Then we will continue seeing the deleterious effect of ALDFG on wildlife and ecosystems, and the economic and social impacts of this discharged gear. Then we will see the magnitude and the geographical trends and the fate of ALDFG in the marine environment. We will finish this lesson looking at some existing measures to reduce the problem of abandoned nets. Marine litter, as also known as marine debris, is human-created waste that has deliberately or accidentally been released in sea or in the ocean. Of particular concern is plastic litter, as it represents a large part of marine litter. Plastics are a diverse group of synthetic polymers that have their origins in the late 19th century, but which really came to the fore in the mid-20th century. Their low density, durability, excellent barrier properties, and relatively low cost make plastics ideal materials for a wide range of manufacturing and packaging applications. Their versatility has seen the amount of plastic produced annually increase rapidly over the last few decades to an estimation of about 400 million tons in 2023. And this total continues growing today. So given its inherent strength and durability, plastic persists in the marine environment for indefinite periods of time. Furthermore, plastic low density means that they are readily dispersed by water and wind, sometimes traveling thousands of kilometers from source areas. As a result, plastic wastes are now ubiquitous pollutants in even the most remote areas of the world. The analysis of the composition of marine litter is important as it provides vital information on individual litter items, which in most cases can be traced back to their sources. Sources of marine litter can be characterized in several ways, and one common method to classify marine litter sources are either land-based or ocean or sea-based, depending on where the litter entered the sea. Land-based sources include mainly recreational use of the coast, general public litter, industry, harbors, and unprotected landfills and dumps located near the coast, but also sewage outflows. Introduction by accidental loss and extreme events. Marine litter can be transported to the sea by rivers and other industrial discharges and runoffs, or can even be blown into the marine environments by winds. Ocean-based sources or sea-based sources of marine litter include commercial shipping, ferries and lines, both commercial and recreational fishing vessels, military and research fleets, pleasure boats, and offshore installations such as platforms and aquaculture sites. Some items can be attributed with a high level of confidence to certain sources, such as fishing gear, sewage-related debris, and tourist litter. So-called use categories provide valuable information for developing reduction measures. It is generally assumed that most of the plastic waste enter the world's ocean from land-based sources. Close to or on the shore, the majority of litter originates from shoreline recreational activities, but is also transported by the sea by currents. In some cases, marine litter density on beaches can be increased up to 40% in summer because of high tourist numbers. Broad-scale quantification generally report that 80% of litter in the world's oceans came from land, and therefore 20% comes from the sea. But this is often cited statistic which is not traceable to a published scientific paper or technical report. Other statistics indeed indicate that fishing activity comprises less than 10% of global marine litter by volume, with land-based sources being in the predominant cause of marine debris in coastal areas, and merchant shipping being the key sea-based source of litter. However, a number of estimates suggest very different contribution of fishing activity to total marine litter based on locality. In some areas, for example, in the North Sea or in the Baltic Sea, but also in some areas of the Mediterranean Sea, the large diversity of items and the composition of the litter recorded indicate that major sources of marine litter is ocean-based. In some cases, litter can clearly be attributed to shipping, sometimes accounting for up to 95% of all litter items in a given region, a large proportion of which originates from fishing activities, often coming in the form of derelict nets. Once in the sea, marine debris, and including fishing-related debris, can be found beached or on the shoreline, floating on the ocean surface, or on the seafloor. Oceanic surface circulation determines marine litter being accumulated in specific areas of the ocean, including the convergence zones of each ocean hemibasin, and along the coast of the tropics, and particularly those of southern Eastern Asia, where the largest worldwide emitters of oceanic plastic pollution are, namely China, Indonesia, Philippines, Vietnam, and Sri Lanka and Thailand. Data on beached marine litter is derived from various approaches based on measurement of various litter categories and samplings on transects of variable width and length that can be parallel or perpendicular to the shore. Floating macrolitter is generally monitored by visual observation from ships, but results from towel nets are also being reported. Beached and floating litter is physically degraded by biological, photic, and chemical processes into smaller fragments until becoming microplastics, which is often defined as the size fraction smaller than 5 millimeters. This fraction requires different monitoring techniques, such as surface net trawls, and are not the subject of this lesson. Today, we will mainly deal with the seafloor litter. This fraction of marine litter is particularly important because the majority of litter items sink directly on the seafloor, and even low-density polymers such as polyethylene and propylene may lose buoyancy under the weight of the falling. Changes in the nature, presence of abundance of anthropogenic debris on the seafloor is much less widely investigated than sea surface partners. Furthermore, until few years ago, studies typically focus on continental shelves, as deep-related difficulties such as the inaccessibility of this environment and the cost needed to explore this area rarely allow for research in deep waters. Strategies to investigate seabed debris are similar to those for evaluating the abundance and composition of benthic species, and studies on benthic fauna and seafloor litter are generally conducted in parallel. The main investigation method include acoustic approaches, for example, side-scan sonar, but this method do not enable discrimination of different types of debris on the seafloor, with the exception of metals, and may not record small objects. Trawling is often used and is considered the most adequate method until few years ago, but this method presents several shortcomings. For example, nets were primarily designed to collect organisms, leading to sample bias and underestimation of benthic litter quantities. Trawling, in addition, cannot be used in rocky habitats or on a hard substrate. Furthermore, it does not allow for a precise localization of individual items along the trawling route. And finally, samples collected from trawls are likely to underestimate debris abundance and may miss some types of debris. I would also add that trawling does not enable the assessment of impacts of litter on the habitat, and it contributes itself to impact on the seafloor. And this kind of impact is often more severe for the benthic fauna than the litter items caught by trawl. More recently, remotely operated vehicles and towed camera systems were increasingly used for deep sea surveys. And these methods can be deployed on all substrate types and depths, allowing collecting more detailed information on the position of the litter, the interaction with the seabed, and the impact of organisms. And in addition, these methods allow also to collect very nice images of litter. This table reports some of the example of comparison on seafloor litter density among different basins worldwide. The density of marine debris is generally expressed as weight per unit area or number of items per unit area or per linear distance. Information on litter weight characterizes trawling surveys, whereas the latter two methods allow comparison between trawling and ROV studies. Plastic debris were found on the seabed of all seas and ocean, and the presence of large amounts has been reported, but remains uncommon in remote areas such as Antarctica, for example, and particularly in deep waters. The geographic distribution of debris in the ocean floor is strongly influenced by hydrodynamics, geomorphology, and human factors. Mediterranean sites, for example, you can see it here in the table, show the greatest density owing to the combination of a densely populated coastline, shipping in coastal waters, and also negligible tidal flow. Moreover, the Mediterranean is a closed basin with limited water exchange through the Strait of Gibraltar. From this table, you can also see that generally litter density is higher in coastal seas because of the circulation patterns and also because of the extensive rivering input. Large rivers are responsible for substantial input of debris to the seabed. However, debris that reaches the seabed may have been transported over considerable distances before sinking to the seafloor. Indeed, some accumulation zones were identified far from the coast. Also, continental shelves are considered as accumulation zones for marine debris, and several authors consider submarine canyons as a conduit for the transport of marine debris into the deep sea. And higher density at the bottom were also found in particular areas, such as those around rocks, wrecks, as well as on depressions or channel. A great variety of human activity, such as fishing, urban development, and tourism, contribute to the distribution pattern of debris on the seabed. Debris from the fishing industry is prevalent in fishing areas. We can introduce now the right term to define the abandoned nets. This kind of items can represent major components of marine litter, and several terms have been adopted to identify these materials. And the term abandoned, lost, or otherwise discharged fishing gears, ALDFG, is considered the most appropriate and comprehensive one. During this lesson, and we will use this, we will adopt this term, and I also suggest you to prefer this term to other terms. For example, the term derelict fishing gears is sometimes used as a synonym of ALDFG, but this term does not imply how the gear ended up in the ocean. Otherwise, the term ghost gear or ghost fishing gear are also often used synonymously with the ALDFG, but these terms specifically define the activity of entangling organisms, whereas not all the abandoned, lost, or otherwise discharged fishing gears have these abilities. So, with the abandoned fishing gears, we intend considering those fishing gears over which the operator or owner has the control and could retrieve the gear, but deliberately it decide to leave the gear at sea due to force majeure or other unforeseen reasons. Lost fishing gears are those fishing gears over which the operator has accidentally lost control and that cannot be located or retrieved by the operator. Discharged fishing gears means that the fishing gear is not released at sea without, the gear is released at sea without any attempt for further control or recovery by the operator. I also provide to you definition of fishing gears you can find here at the bottom. So, as you can see, the term abandoned, lost, or otherwise discharged fishing gears provide a wide encompass a lot of different situations, better defining the problem of fishing gears found on the seafloor. Whereas the other terms, including derelict fishing gears and ghost gears, provide also allow only to identify specific category of ALDFG. I would like to dedicate now a few slides to the type of fishing gears and their main components. I think that this kind of knowledge will help you to best define what ALDFG are. The International Standard Statistical Classification of Fishing Gear provide useful broad categorical terms and description for fishing gears globally adopted. But there are hundreds of other specific fishing gears subtypes employed by fishers all around the world that are impossible to include in a list. And these more specific gear types and variation often originate from traditional fishing cultures and are developed by fishers accordingly to specific capture efficiency requirements. Furthermore, fishing gears may be additionally modified by fishers in accordance with the fishing method, with the gear structure and the different operational approaches. And for these reasons, we will now focus only on some type of gear particularly important in the Mediterranean Sea. The first group of fishing gear I am going to present include active gear. Active gear means that the gear actively encircling the target, as in the case of the purse seiners and the seine nets, or the gear move toward the target, as in the case of the trolling nets. These gears must resist to high stresses, and they are pulled for long periods of time and are dragged for long distances. Thus, their nets must be particularly strong. The netting is generally comprised of small mesh size to minimize fishing become enmeshed. Netting materials are usually comprised of polyamide, polyester, and generally they have densities higher than that of the seawater, and these allow to increase the netting sink velocity. Surrounding nets are deployed on the sea surface, and the contact with the seabeds are rare. Trolling net, on the contrary, are demersal gear strongly interacting with the seabed, and thus the probability to entangle the seabed and be lost is higher than those of the surrounding nets and the seine nets. Here you can see some nice pictures of abandoned purse seiners and trolling nets. You can see that this category of ALDFG could be easily identified from their shapes, the presence of particularly structure, for example, the good ends of the trolling nets, and from the thickness of the net meshes. A second category of fishing gear is represented by gill nets and other post nets, which are considered passive gears. This means that they do not move toward the target, but is the target itself which moves into the gear. A set gill net is a long rectangular single-walled netting anchored or otherwise fixed to the seabed, catching fish when they come in contact with it. The The set gillnet is held open vertically in the water by a head rope, usually with floats, and by a foot rope weighted with sinkers. The net is kept in position by anchors or other weights, and usually at both ends on the surface there are buoys or high flyers. The set gillnets is the most common type of gillnet and is also referred as the bottom gillnet or simply gillnet. Drift gillnets are a type of gillnet that is not fixed on the seabed but allowed to drift with the currents. Drift gillnets have been reported as a concern for non-target species such as marine mammals, seabirds, and turtles. And as a consequence, the United Nations banned the use of large-scale drift nets with length higher than 2.5 kilometers long. And this occurred in 1991. On the other hand, drift gillnets usually do not have an impact on the seabed. A trammel net, you can see a picture here, a scheme here, is a gillnet that has 3 layers of netting with 2 other layers of large mesh netting and 1 inner layer of slightly hung small mesh netting. And this particularly composition of net allow to entrap the fish in a pocket in a pocket created by the small net, the small meshed net among the 2 large meshed nets. When a fish pushes the small mesh netting through one of the other layers of large mesh netting, the netting forms a bag, a pocket that can retain the fish. Trammel nets are usually set on the bottom in a similar manner of the set gillnets and are widely used as a small-scale fishing gears all over the world for various species. A combined gillnet trammel net is a bottom set net consisting of a regular gillnets in the upper part of the net to catch semi-demersal or pelagic fish, and a trammel net in the lower part of the net to catch near bottom fishes. Here again you can see some example of abandoned or lost gillnets and trammel net. You can try to spot which one is a gillnet and which one is a trammel net. Generally, both types of gears can be made in monofilament nylon or woven fibers comprised of polyether sulfone, nylon, polyamide, or polyethylene, which are non-biodegradable. You can see that these are for sure gillnets, and these ones are trammel nets because you can see that they have multiple net panels with large mesh size and smaller mesh size. You can see here, here, and here is very clear. And With the introduction of synthetic materials in 1950s and 60s and subsequent reduction of price, the use of gillnets made the synthetic materials drastically increasing. And this increase is also attributable to the low visibility of monofilament twine. And you can see here very clearly from this picture. And another fact which is important is that gillnets and entangling nets are usually untended. This means that they work without the presence of a boat, and this increase the probability of gear loss, and thus increase also the contribution to marine plastic pollution. Another kind of passive gear is represented by traps, and traps are stationary structures of many shapes and sizes into which fish are guided or pushed by the current or drawn into the gear by bait or other attractants. A pot or a trap, a pot is a particular type of trap characterized by a small enclosure that attract fish through one or more entrances that allow the entry of fish but prevent the fish to escape. Pots are usually set on the bottom with the bait, singly or in a fleet of many pots, as you can see in this figure. And the pots are connected by a rope and to a marker on the surface. And they can be hauled by hand or using a mechanized pot hauler. They can be of any shape and be made of many materials. The pots represent an important type of gear, especially in the fishing of crustaceans like lobster, crabs, and shrimps. And similarly to gill nets and entangling nets, pots are untended fishing gears, and they are capable of catching fish and other marine animals without the presence of the vessel. And as a consequence, gear loss is extremely common, and they contribute consistently to marine plastic pollution. The last type of gear we are going to discuss are those that use hooks and lines to catch fish. They include end lines and end operated pollen lines. I put this image as a reference, and they represent the most important recreational fishing gears. It can be operated from the shore or from a boat, as in the case of this picture, and they can be actively operated by hands or mechanically using powered reels or drones. A second type of hooks and line gears is represented by long lines, which are fishing gears where hooks and where hooks are connected to branch lines which are then attached to a long horizontal main line at certain intervals. You can see some example of long lines in these pictures. The number of hooks and the length of the main line depend on the scale of the operation and the area of fishing grounds, ranging from a few hundreds meters in coastal set long lines to more than 80 kilometers in large-scale reef pelagic long lines. Long lines can be anchored or otherwise fixed on the seabed at either end of the main line, and in this case they are called set long lines, or they can drift passively with the currents, usually with a boat, as in this case. Drifting long lines usually fish near the surface of the sea, and for this reason their impact on the seabed is considered very low. A particularly type of long lines are the vertical lines, which are lines set vertically with one or more baited hooks attached. A buoy is usually attached to the line at the surface to indicate the position of the gear. A weight also is attached to the bottom of the line, and the weight can be located on the seabed to secure its position of the line, or otherwise it can drift in the water without attaching to the seabed. Several lines are often deployed in small concentrated areas, such as seabounds, and when the weight touch the seabed, as in the case of the set long lines and the vertical lines, the probability of entangling the seabed is high, and often gear loss occur, as you can see in this picture here. In this slide, I just want to recap which are the main components of the fishing gears, following the different portion of the gears. For example, netting are largely comprising mono or multifilament fiber polymers woven into knotted or and knotted meshes. The main types of netting polymers include polyethylene, polyamide, and polyethylene sulfone, which are non-biodegradable. And here you can also find which are the main material accompanying the ropes and line, floats and buoy, the sinkers, and the metallic materials which constitute the different portion of the fishing gears. I would like now to present some reasons why fishing gears are abandoned, lost, or otherwise discharged, and a range of environmental, conflict-based, management-related, and operational causes result in the loss of fishing gears. The potential for fishing gear to become lost depends on the operational and gear types context, such as the depth where the fishing occurs, whether the gear is tendered by a vessel and how often, the gear size, the soak times, and the weather condition. Another important factor is whether the gear contacts the seafloor or other obstacles present on the seabed. For example, bottom gears such as bottom trawls, set gill nets, trammel nets, and long lines are often more at risk compared to midwater or pelagic gears, because these gears are more likely to become snagged upon obstacles on the seafloor. Passive and unattended gear types, where fishers have less control over the gears while fishing, such as many types of traps, gill nets, and entangling nets, are also more likely to be lost, as there is less opportunity for a fisher to intervene to prevent gear loss without active control of their gear. In this sense, pots are generally more likely to become lost compared to other trap types, often due to the influence from bottom contact, weather events, interaction with other vessels, and relatively large number deployed. Hooks and lines are additionally often lost as a result of normal operation. For example, regular bite-off from wildlife or breakages from detachment of lines into fragments because of contacts with the sea bottom. In recreational fisheries, line and lead weights are usually commonly discharged or lost during tackle manipulation. Among the environmental causes, seafloor topography represents the major cause of gear to become snatched and make impossible or difficult to recover it during fishing operation. When the gear is snagged on the seafloor obstruction, fishers may attempt to recover as much of the gear as possible before cutting the remaining gear and thus leaving the snatched portion and the section of the gear leading to the sea surface at the snag location. Extreme weather, and in particular strong currents and heavy winds, can sweep the gear of position and this fact make difficult or impossible to relocate the gear. Extreme cases occur during natural hazard events such as hurricanes and tsunamis, which can lead to large localized and regional accumulation of ALDFG. Dangers associated with the fishing operation in inclement weather are may cause gear abandonment in addition to gear loss, as fishers may choose not to retrieve their gear due to the hazard present. Finally, among environmental causes of gear loss, wildlife interaction with fishing gear can determine fall damage and move gear of position, which can lead to the loss of the gear. This is more likely to occur with static gears, such as longliners, set gill nets, and pot gear. Example of wildlife interaction causing ALDFG include large whale entanglements in vertical lines and long lines, as well as large sharks and dolphins and sea turtle, etc. Conflicts with other fishing gears and vessels represent a major cause of ALDFG, followed by poor weather condition and entanglement on seabed obstruction. Gear conflicts primarily occur in areas with high concentration of fishing activities. Passive gear, such as spots and set gill nets, are particularly prone to being towed away or damaged, either unintentionally or deliberately by active gear such as trawls or dredges. Relatively lighter active gear, such as trawl gear, can become snagged, broken, and eventually abandoned or lost due to the entanglement in passive gear, such as spots, bottom long lines, or anchored nets. When gear items are set too close to other gear, even from the same type of gear, and even when the gears are properly marked, gear components such as lines can wrap and become entangled with other nearby gear items. Our crowded fishing grounds can additionally put pressure on fishers to set gear in marginal areas, which can eventually lead to gear loss from other causes. For example, gear snagged on seafloor obstruction. Popular fishing grounds can also lead to conflicts among fishers in the form of tampering, sabotage, vandalism, and theft of fishing gears, all of which can cause ALDFG. Finally, high concentration of ALDFG from commercial and recreational fisheries occur in high vessel traffic areas. Passing vessels of all kinds can strike marker buoys and their associated lines, thus producing ALDFG. In addition, when multiple fisheries using different gear types are allowed to fish on the same fishing grounds without spatial or temporal restriction, the likelihood of gear loss increases from overcrowding, competition, and conflict among fisheries. Thus, fisheries management and regulation are a primary role in the prevent of ALDFG. The lack of adequate port waste reception facilities for end-life fishing gear can cause ALDFG via deliberate discharging of old, damaged, and unwanted gear at the sea due to the time cost inconvenience of gear correct disposal. Furthermore, no gear marking requirements or minimal requirements that do not include sufficient owner identification or are not connected to a centralized gear loss reporting system can result in an increased propensity by fishers to abandon or intentionally discard their fishing gear. Deliberate gear abandonment or discard is often related to illegal or unreported fishing. IUU contributes to abandon, lost, or otherwise discharged fishing gears in different ways. For example, gear abandonment when operating in marginal or unauthorized areas, operating in poor weather or at night to conceal activity, and finally, abandonment of illegal fishing gear from the boat where inspection authorities approach the vessel. Abandoned, lost, or otherwise discharged fishing gears often simply results from a normal fishing operation on board a vessel or from common operational errors by fishers. For example, the foot rope on a bottom trawl may break due to the constant wear on the seafloor if it not properly maintained or replaced in a timely manner. Hooks and part of branch lines or long lines gear are frequently bitten off by target and non-target species. So the possibility of normal losses are high common during fishing activities. Gear losses can also be associated with the level of operator and competency, expertise, and knowledge of the crew. And combinations of risky environmental conditions and gear types more prone to gear losses can increase the likelihood for ALDFG, such as the use of demersal gear on a rough seafloor in inclement weather. Gear may be cut adrift and discharged for safety reasons during fishing operation occurring in severe weather conditions or when gear inadvertently drifts into high traffic shipping lanes. Finally, vessels may deploy more gear than can be retrieved on a trip, which can lead to longer soak times and, in turn, greater potential for gear to become lost due to a variety of factors such as conflict, strong currents, and inclement weather. Now we will discuss the deleterious effect of ALDFG on wildlife and ecosystems. Most fishing gears is designed to catch target species, but this attribute can result in negative impact the target and non-target species when the gear is lost, especially in the case of gillnets and pots. Some gears, such as gillnets and pots, have the ability to ghost fish. In several cases, there is a common tendency to continue fishing with a declining catch as the gear becomes less effective, although the duration of this cycle can vary widely depending upon the local environmental condition. Overall catch rates of ALDFG vary so greatly that a global estimate would be meaningless. Several studies, however, considered long tangle nets to catch around 5% of the total commercial catch. Other gears, such as lost trawls, rarely ghost fish, but have other kind of impacts, such as smothering the benthos and damaging delicate habitats, such as coral reefs or coralligenous reef in the Mediterranean Sea. Lost long lines also rarely ghost fish, but may become entangled, or the hooks may be embedded in the bodies of seabirds, for example. The state and the position of a net from its initial loss of control is a key variable in determining its catching efficiency. Abandoned nets or pots may be set for maximum fishing efficiency and will thus leave higher ghost fishing catches. On the other hand, discarded nets may collapse immediately and will thus have lower initial fishing efficiency. Nets and pots may also be discharged in areas where they have less potential to ghost fish. And once ALDFG has lost its burden of captured fish and marine growth, it has the potential to regain its shape and start fishing again. Accumulated catch may act as a bait for other species that get entangled or entrapped in the gear. As a result, ALDFG typically increasingly catches other fish and shellfish species that may or may not have a commercial value. Interactions with the marine wildlife can occur via entanglement, whereby ALDFG entangles or entrap animals and their habitats, or ingestion, whereby ALDFG is intentionally or accidentally ingested. Entanglement and ingestion become particularly significant when considering rare or endangered sea mammals, turtles, or other animals. All the 7 marine turtle species, 66% of marine mammal species, and 50% of seabird species have been reported to have been entangled with ALDFG or ingesting plastic marine debris. There are few comprehensive global studies on the overall significance of these, but specific studies have indicated that ALDFG may be a significant cause for mortality for some species at local level. Impacts from entanglement include a reduction in food intake and limitation in movement, wounds on body parts that can result in secondary infections, and death from starvation following compromised feeding capacity due to the entanglement. Record on ALDFG ingestion require detailed analysis, including dissection of gastrointestinal tracts to determine the material ingested. Thus are more difficult to collect than those on entanglement. All sea turtle species, more than half of marine mammals species, and 40% of procellariform species, which are albatrosses and petrels, have been reported to suffer from fishing gear ingestion. This review on incidental catch of vulnerable species in the Mediterranean and Black Sea fisheries provides additional interesting and useful information on this matter. ALDFG that settles on seafloor habitats, especially in rocky and coral substrate, can adversely affect surrounding benthic communities. Once the gears are settled at the bottom, the coral and other benthic organisms beneath the nets become smoothed by the sediments, and extensive mortality events may occur. The magnitude of such events are strongly correlated with the characteristic of the benthic communities. For example, some benthic areas are characterized by complex three-dimensional communities such as coral reefs, Gorgonian forest, and sponge grounds, which attract a rich associated fauna and provide essential ecological roles in marine ecosystems. These communities are often named marine animal forests because of they resemble the terrestrial counterpart and provide similar ecological roles. Because of the high abundance of commercial species, often with large-sized specimens, these communities are usually targeted by commercial and recreational fisheries. The effect of ALDFG on marine animal forests are particularly severe and can produce a significant adverse impact. This means that the long-term natural productivity of an ecosystem is degraded on a more than a temporary basis, compromising the long-term integrity and function of complex communities and habitats. In topographically complex sites, demersal fishing gears can easily remain entangled on the hard bottoms and benthic species, thus damaging these habitats and remaining abandoned on the seabed. Once lost on the seabed, this gear continue to damage megabenthic species, and nets can directly suffocate a large area of seabed. In this case, ROV exploration allow to report widespread impact of abandoned fishing gears on Mediterranean benthic communities. And emblematic is the case of the Maledetti Shoal in the Ligurian Sea, which is a vertical wall located between 50 and 90 meters depth, dominated by a dense Gorgonian forest. Here, the artisanal trammel net spine lobster is employed on the complex topography of the sea bottom in close intimacy with the vertical wall, causing high risk of gear loss. Here, extremely high abundance of ALDFG are reported, accounting for about one items for every 2 square meters, and entanglement is the most common type of impact, affecting 40% of the Gorgonians of the Maledetti Shoal. Furthermore, the continued abrasion of lines and nets on anthozoans, particularly Gorgonians, can produce tissue abrasions, leading to bacterial infection and necrosis. Necrotic areas are rapidly colonized by epibionts, and their weight can lead to branches to break, causing additional stress and mortalities. High levels of epibiosis on coral species have been related with areas high impacted by demersal fishing activities. Entanglement with the lost lines, causing extensive damage to gorgonians in the Portofino marine protected area, again in the Ligurian Sea, have been characterized by divers at distance of 25 years. Entanglements cause a significant reduction in gorgonian density and size in this arc of time. Similar damages were recorded in several areas of the Tyrrhenian Sea. Thus, the deleterious effect of ALDFG on wildlife and ecosystems include also the introduction of synthetic materials within the trophic net. But this issue is poorly understood at present. ALDFG also causes economic impacts on fishers and associated fisheries, including direct and indirect losses. The direct financial losses include the loss of the gear itself and any target species caught in the gear, which is not longer available for commercial catches. The magnitude of this loss depends on the gear type, amount of gear loss, and the commercial importance of the target fishery. The indirect or hidden costs are multifaceted and include lost fishing opportunities due to the non-availability of gear in hand, especially for the fishers who do not have spare gear available for an immediate replacement, the loss in value due to the ghost fishing by ALDFG, no longer available for fishers to catch and from which to profit in the future, the retrieval costs, including time and fuel costs to search for the lost gear, and the cost incurred by fishers to replace lost gear. ALDFG negatively impacts people's quality of life in several ways by reducing recreational opportunities, loss of aesthetic value of recreational facilities and natural areas, such as the loss of clean beaches and coastal areas. Secondary impacts from ALDFG damage to marine biota and bedding habitats can result in compromises the availability and effectiveness of ecosystem services for coastal communities. Finally, it must be noted that at least one incident of a vessel sinking as a result of debris entanglement has been reported, resulting in significant loss of life. The Korean Maritime Accident Investigation Agency reported that the ferry Sohee, sinking in 1993, was caused in part by fishing ropes around the propellers, leading to 292 human fatalities. At present, there is no global geographic assessment of quantities and categories of abandoned, lost, and discarded fishing gears that allow for definitive identification areas of high concentration or accumulation of ALDFG. Nations or regions where ALDFG surveys and research are being conducted and published provide a snapshot of where ALDFG exists and is of sufficient concern to drive scientific inquiry. This publication provides evidence for where this gear occurs, but cannot be extrapolated to any kind of global measure of presence, absence of relative density due to limited ALDFG presence and absence data. This means that areas or regions with sparse to no data do not indicate less or no ALDFG. General estimation on the rates of permanent net loss appear to be rather low, with some exceptions related to regional fisheries. This is largely because most nets are deployed in shallow waters, and after they are first lost, a significant proportion of nets are then recovered through the use of global position systems. Fishers typically go to considerable lengths to recover nets given their cost. However, because the total length of nets being set is high, the total length of netting permanently lost may be significant, although exact figures are not available. Estimation of ALDFG entering annually the ocean varying between 1 and 640,000 tons indicated that a more accurate estimation on the proportion of marine litter that is ALDFG is urgently needed. Some efforts have been made to evaluate the gear-specific relative risk from derelict gear to rank order fishing methods. The evaluation is based on derelict gear production rates, gear quantity indicators of catch weight and fishing grab areas, and adverse consequences from derelict gear. The latter accounted for ghost fishing, transfer of microplastic and toxin into food webs, spread of invasive alien species, and harmful microalgae, habitat degradation, obstruction of navigation, and in-use fishing gear, and coastal socioeconomic impacts. Globally, mitigating higher risk derelict gears from gillnets, tuna pure seine with fish aggregation device, and bottom trawl fisheries achieve maximum conservation gains. In the last decades, ROV surveys in the Western Mediterranean basin have provided evidence for fishing impact and ALDFG as omnipresent features in all the surveyed localities. In light of this evidence, it seems highly probable that pristine deep coral forests no longer thrive in certain exploited rocky areas of the Mediterranean basin. The structure and distribution of the existing assemblages may represent the result of a great reduction in their original abundance, as well as geographic and bathymetric ranges. There have been attempts to use the ROV footage to characterize local situation. These attempts are often based on the quantification of litter density and the identification of litter items. The majority of the debris is clearly ascribable to fishing gears, mainly attributable to long lines. And these patterns are also common in similar ROV studies conducted in deep sea areas of the Atlantic and Pacific Oceans. The low amount of lost net occasionally recorded at the base of the shoals or along gently slopes suggested that the explored areas are mainly exploited by longliners, which, accordingly to Italian legislation, may be used both by professional and recreational fishermen. This data suggested that recreational fishing may have a major role in affecting benthic communities, despite the fact that large number of people fishing recreationally, no estimates of ALDFG resulting from recreational fishing exist. The nets observed on the sea bottom are generally attributable to artisanal fisheries, being often represented by set gill nets and trammel nets. This information highlights a major role of small-scale fishery in the production of ALDFG. I would like now to discuss some facts regarding the fate of ALDFG in the marine environment. ALDFG are generally made of aliphatic polyamide, as we have seen before, nylon, and due to their long chain polymer structure and high molecular weight, they persist in the marine environment for a long time. Megabenthic communities actively respond to their presence. Since ALDFGs provides a new hard substrate for several marine organisms that settle on the free surface as biofouling. Biofouling, composition and succession have been studied over several types of material, but only a few studies investigate its composition and development on ALDFG. A comprehensive understanding of the diversity and the colonization pattern of the organisms settled on these materials would provide useful information on the fate of ALDFG and the responses of megabenthic communities to their presence. Also, the ability to correlate the time spent at sea with the level of colonization would allow to identify putative age of the lost gear, opening up an important perspective in the field of managerial and forensic sciences. ALDFG age provide useful information for the monitoring and the study of legal as well as illegal, unreported or unregulated fishing activities. And it is essential to characterize changes in time of the fishing impact in determinated areas. Field experiments have been conducted on abandoned lines and nets along the cliff of the Portofino promontory, again the Ligurian Sea. And these experiments indicates that nylon ALDFG are rapidly covered by biofouling organisms, which reach the maximum cover values in about 1 year. Some differences in biofouling diversity are related to the type of fishing gear, potentially referable to the amount and complexity of their surface. For instance, the nets are made by many woven filaments that notably increase the availability of surface and the three-dimensional complexity of the gear. And the nets present the highest diversity with respect to simple lines. The month, season in which the gear is lost certainly influence the initial composition of the biofouling community, as the surface of the gear will be exposed to different larval recruitment and survival rates of the colonizers. Substantial changes in the annual biofouling community are related to the seasonal cycles in light intensity and water temperature, determining inverse fluctuation in the macroalgal and hydrozoan communities. And such fluctuations are strongly affected by the depth of the fishing gear and are expected to become less clear at higher depths. Biofouling composition and succession have been studied over several types of material, but only a few studies investigated this composition in the ALDFG. And by considering the diversity, biomass, cover patterns, and community composition, it is possible to identify 4 general stages of colonization with specific reference to temperature, latitudes, and subtidal depths. In the first stage, the process of biofouling formation begins immediately upon immersion, with the formation of a macromolecular organic layer. This conditioning biofilm is composed of proteins, polysaccharides, proteoglycans, and provide a sticky surface for microorganisms to adhere to. After a few hours, bacteria and microalgae settle on the substrate as a primary colonizers, and through the secretion of extracellular polymeric substrate, deeply modify the nature of the biofilm. After 1 week, the secondary colonizer, represented by macroalgal, spore, and protozoans, settle on this surface, followed within the second and third week by larvae of invertebrate metazoans, which represents the macrofoulers, leading to a more complex biological community. However, in this phase, the community is extremely simple, being characterized by low density, low abundance, cover, and biomass. A transitional stage occurs from 2 to 4 months of immersion. Cover increase up to 50%, and macroalgal biomass and diversity rise considerably. Carbonatic organisms are rare, being represented only by few delicate bryozoans. From 5 to 11 months of immersion, cover reaches value ranging from about 50% to 80%. Small-sized calcified organisms become frequent in this stage, increasing in number and diversity. They are generally represented by encrusting species with limited vertical growth, such as coralline algae and serpulid polychaetes. Finally, between 1 and 3 years, cover values generally reach 100%, 80, 100%, and the carbonatic species become conspicuous. Serpulid polychaetes, bivalves, and bryozoans are common and reach higher size. For example, Pentapora, the bryozoans Pentapora fascialis and Retteporella become large. All plastic materials, including ALDFG, degrade through fragmentation and microplastic releasing. It's interesting to note that the study conducted along the Portofino promontory indicated that no deterioration signs or weight loss were detected after 38 months of immersion at 30 meters. By contrast, other studies report that nylon ropes lose up to 1% of their mass per month when abandoned for 1 year at 10 meters depth in the Firth of Sea Clyde in Scotland. This could be explained by the different bathymetric range of the two experiments and by the fact that 10 meters depth represent a depth where UV radiation, wave motion, and sediment abrasion could provide could facilitate the degradation of the gears. At the same time, in the case of Portofino, the massive and fast developing of compact carbonatic cover could have greatly reduced the degradation process of the nylon surfaces. Encrusting organisms like algae, serpulids, and bryozoan form at this depth a thick and hard envelope engulfing the gear in the environmental matrix and plausibly extending its deterioration time. A variety of measures aimed at the prevention, mitigation, or cure of ALDFG, many of whom have been implemented across the globe. Some measures, such as gear recovery programs, are specific measures to tackle ALDFG, while others, such as effort restrictions, for example, pot limits, soak time limits, may be implemented to tackle more general problems of overcapacity, but may have the additional benefits to reduce ALDFG. The most appropriate measure to tackle ALDFG is more likely to be identified if the type and cause of ALDFG is known for any particular situation. For example, if gear conflict is a key cause of lost gear, better spatial management to avoid conflict should reduce the incidence of ALDFG. Where discarding of unwanted or damaged gear at sea is seen to be an issue. A lack of accessible reception facility may be a key factor in the provision of those facilities should reduce ALDFG. The range of applicable measures move from preventive avoidance measure, most effective, on the left of this graph, to curative measures on the right. As the figure indicates, preventive measures are more targeted to specific types of ALDFG, while curative measures can address ALDFG from numerous causes. Many measures are also of limited effectiveness in isolation, and it is therefore suggested that a suite of measures should be implemented. Curative measures could be implemented promptly, while preventive measures would be implemented once the causes of ALDFG are known. For example, a comparatively intensive gear retrieval program may be undertaken initially to remove the immediate problem, but this should be supported by measures to prevent the recurrence of ALDFG in the area. This can be achieved through awareness raising, communication between fishers, and provision of reception facilities. With this, I finished this presentation. I would like to see again with you the measure contents we have been through. We have seen which are the measure kind of marine litters, the sources, the distribution, and the methods of study. We have defined what ALDFG are. We can see the measure type and components of fishing gears, and we have seen which are the measure reasons why fishing gear is abandoned, lost, or discarded. We have passed also the deleterious effect of ALDFG on wildlife and ecosystems, and also the economical and social impacts. We have also observed some facts about the magnitude and the geographical trends in ALDFG, and we have seen also the present knowledge regarding the fate of ALDFG in the marine environment. And finally, we have seen which are the existing measures to reduce the problem of ALDFG. With this, I conclude this presentation, and I am open to any kind of questions.
Okay, thank you, Francesco. Yes,